When we are asked to find the limit at infinity of an expression that involves a summation, we'll want to work inside the parentheses out, where we take care of rewriting our summation using the rules and the formulas for summation, so that we have this just as an expression in n's, or whatever your variable is of your limiting process, and then take our limit as our last step. Now, if you haven't looked at the segment on the rules and properties of summation, or the formulas of summation, or if you haven't reviewed them from your textbook, you'll want to do that before watching this segment. But if you've already viewed it, or if you have it where you've got those properties and those formulas written out, then as we go through those steps, you'll want to make sure you refer to them so that you know where I'm getting the information from each step. Okay, so let's look at this problem. We have the limit as n approaches infinity of our summation k equal 1 to n of the quantity 2 plus 3k over n times 3 over n. So when I look at this whole expression, I need to rewrite it without my summation. My variable, or my index of summation, is the k, and I notice that is present in this second term. The factor that has the multiplication of 3 over n that doesn't have the k in it, this is a constant in the summation process. So one of the first things I like to do is just to bring this factor that doesn't have the k involved, or whatever the variable is of your summation, out in front of the summation. I can't take it out in front of the limit, however, because it is the variable for the limiting process. So this 3 over n factor I'm going to bring out in front of the summation, and then I have the summation k equals 1 to n of my 2 plus 3k over n. Now the next thing I see is that I have a summation of an expression that has more than one term. And I notice that I don't have an exponent on here. If I did, I would need to make sure that I multiplied out to have it term by term. So since I have separate terms, I can go ahead and write what I had from the previous step. And then now what I'm going to do is take the summation k equal 1 to n of my first term 2, plus the summation k equals 1 to n of my second term, 3k over n. One of our rules of our summation is that if we're taking the summation of an addition of two formulas or a subtraction, I can take the summation of the first and then use the plus or the minus between and the summation of the second. Okay, next what I want to do is, I see that I do have a summation k equal 1 to n of just a number, and I have a rule that a formula that I can replace that one with. And in the second term, it's the summation k equal 1 to n of values multiplied to my k. So I want to bring that 3 over n just in front of this summation, because that's the only term that that particular 3 over n was in. So we have now the limit as n approaches infinity of our 3 over n from this factor that came out in the very beginning, and then times my summation k equal 1 to n of 2 plus, and now this 3 over n is going to come out in front of the summation k equals 1 to n of k. Now, in your formulas for summation, you have a formula for the summation k equals 1 to n of a number. And the formula, shortcut answer for that, is we just take our number times our value at the top. So 2 times n is the formula for that expression. So I have my 3 over n, and then multiply 2. For this summation, my rule is going to be 2 times n, so I have 2n. And I've applied the summation process and gotten the answer in a quicker way from the formula, so I drop the summation symbolism there. And then plus, I have my 3 over n, And then the rule for summation k equal 1 to n of k to the first power is n times n plus 1 all over 2. Okay, now we just need to simplify this before we do our limiting process. In this second term inside the parentheses, I have a common factor of n that can be removed from those two terms. And I could also build and get common denominators in here to make this all one fraction. So I will think of this first term as 2n over 1 and build this top and bottom by 2 to get a common denominator with that second fraction. So we have the limit as n approaches infinity of our 3 over n times, in this first term I have 4n over 2, and then plus, in this next term I have my fraction bar, I have my denominator of 2, and in the numerator I'll have 3n plus 3. Okay, so next what we're going to do is we're going to combine these fractions since we have our common denominator. So that's the limit as n approaches infinity of our 3 over n times 4n plus 3n plus 3 is 7n plus 3 all over my common denominator of 2. We have just a couple more things to do. Next, when we multiply a fraction times a fraction, we just multiply across the top and multiply across the bottom. So that's a limit as n approaches infinity of 21n plus 9 all over 2n. So at this point, we're ready to look at what we do for our limit as n approaches infinity. Now, when we are looking at our limits at infinity, and we have a polynomial in our variable over a polynomial, we look for the highest degree in the denominator. The highest degree in our denominator is n to the first. And then we divide all the terms in the numerator and the denominator by that power on your limiting variable. So n to the first is the highest degree in my denominator. So I'm going to divide my 2n over by n, my 21n by n, and my 9, divide that by n. What I did was I just really built this fraction top and bottom by 1 over n multiplied through the top and 1 over n multiplied through the bottom and distributed. And since I multiplied the top by the same expression that I multiplied the bottom by, as long as I'm not multiplying by 0, I get an equivalent expression to my original, just it looks different cosmetically. So this is the limit as n approaches infinity of, well, 21n over n is 21, plus 9 over n is still 9 over n, and then in the denominator, 2n over n is 2. Now as n goes to infinity, that limiting process of 21 is still 21. As n goes to infinity, a fixed numerator of 9 divided by a value that goes off to infinity, well, when your numerator stays fixed and your denominator gets huge, then that means the overall fraction value approaches 0. And then in the denominator, limit as n approaches infinity of 2 is still 2. So my overall value for that original limiting question is 21 over 2, or 10.5 if you wanted to go to the decimal form.